So in this example, let's find the area between the curves of g of x and f of x. So the first thing that's kind of important to note is we can see the area that we're looking for is just between these two inputs. I'm going to go ahead and leave that point of intersection to you, just setting these two equal and finding where they touch, and I'll include a screenshot of my work at the end of the video. But for this video, we will see that these points of intersection are 1 to 3. So what we are looking for here is we're looking for the area of that shaded region, which is right here. Now, this area, this shape, doesn't really have a formula that we can follow. So the idea is that we're going to approximate it with a bunch of little rectangles. So I'm drawing in a few of them. And we get this idea that the more rectangles that we would use, the better the approximation of that area. So when we see a bunch of rectangles, we're going to introduce the integral sign. So again, when we see that sign, that's telling us, just as like a side comment, to add up a bunch of rectangles. Now we only want to add rectangles between the limits of integration here of 1 and 3, so between 1 and 3. Now for those rectangles, we need a height and a width of the rectangle. Well, the width of the rectangle is up to me. That depends on how many rectangles I want to fit into that interval. So whatever change in x I decide, that's going to be the width of my rectangle. Just going to move that over for a second. Now, the height of that rectangle is what I need to figure out. So let's just pick kind of one rectangle. Let's just use this big rectangle right here in the middle to help us find out the height of that rectangle. So again, we can see the width of that rectangle is going to be whatever I set dx to be. So I'm going to go ahead and erase some of these old rectangles here just so we can see the one that we're looking at. Let's just say we're looking at just this one in the middle as an example. So the width is dx. If I wanted to find the height, well, the height is very easy to see on the picture. The height is right here. I'm just going to label that with an H for height. So how do I figure out that height? Well, the height is the difference between this green line. Now this green line is going to be whatever that value is right there. Well, that's just the y value of this function right here. And it says this function right here is f of x. So this value is going to be determined by f of x. The lower part of that rectangle, so this y value, well, that's just the y value of this other function, right? And this function is described as g of x. So the height of our rectangle right here is just going to be the difference between f of x and g of x. So that height will be determined by taking the output of f of x and subtracting the output of g of x. So we can see then that we'd be able to apply a difference property of our integrals. So we could just calculate the integral from 1 to 3 of f of x and subtract the integral from 1 to 3 of g of x. So I'm going to use my calculator to evaluate some of these integrals, but we're going to draw them on the graph as we do. So if we go to our calculator, the calculator would tell us that this area, which I'm going to write in green now so I can highlight in green, this area would be 5.33 repeating. So I'm just going to use decimals right now to approximate it. So what I'm highlighting in green has an area of about 5.3 units. So then when we go to our calculator, which I'm now going to use blue, when we calculate this second integral, the calculator will tell us that's 2.66 repeating. So I'm, again, just using decimals right now. So that's what I am highlighting in blue. So in other words, if we took this green area that looks like this, that's the area under f of x, and then we subtract away the blue area, which looks like this, what we'd be left with would be just that red stuff, which is what we wanted to originally find the area of. So if we subtract those two numbers, our final answer, and again, I'm just approximating with the decimals, is about 2.667. So here again, we're tasked with finding the area between two curves. So obviously we would need to make a graph of those two curves. For sake of simplicity in this video, I already have it prepared, and it's just going to kind of be inserted right now. But of course, like with these two functions, I don't think it's necessarily crazy to ask you to do them by hand. But here what we have is our graph of the function. So what we're trying to do is we're trying to find the area between the curves. There's actually two different sections of area, right? So between the curves, that means here. And then it also means here. So what you'll notice here is I also did take the time to already find the point of intersection. I'll include the work for that just as a quick little screenshot in the video. So what we're trying to do then is we're going to have to like represent this as some integrals. So what we're trying let's represent this like using some integrals. So let's look at this first area here. So this first area, we associate that with being an integral. So we're looking from the input of 0, in this case, which is a theta, of input of 0 all the way up to that input of pi over 6. So we're going from 0 to pi over 6. Now, if we're thinking about a bunch of rectangles, if we think about the height of those rectangles, so in other words, what is the height of this rectangle going to be? Well, what we can see is that the cosine curve, which is in blue, and our sine curve is obviously in red here. What we can see is that the cosine curve is on top, and the sine curve is on the bottom. So if I wanted the height of those rectangles that we'd use, we'd just simply subtract the two. So I'd take the cosine value, and I would subtract the sine value. That's the height of the rectangles. Now the width of those rectangles are going to be whatever I choose to partition the theta axis down here, so d theta. Now there's more area, so I'm going to add something. Now we're going to look at this area here. So that area, again, is an integral, but it starts at pi over 6, and it ends at the end of our interval of pi over 2. Now the height of these rectangles, like if I just look, let's say like this one right here, this height is going to be determined a little bit different because g of theta is on top on this case, and f of theta is on the bottom. So the height of those rectangles is going to be calculated in a different order. I would take the height at g of theta, and I would subtract the height at f of theta, and that would be the height of all those little rectangles. And again, what is the width of those rectangles going to be? Well, the width of the rectangle is going to be whatever I set it to. Eventually it's going to be infinitely small, and it's going to be some sort of change on the theta axis. So this would be perfect to type into our calculator, which if we do, this will now calculate that area, and I've already typed it into my calculator, and I get 0.5. Now just as another kind of point here, what we could look at is break this down even further, right? We do see those properties. We could go ahead and do this and kind of break down using the sum or the difference properties. And that's what I'm just writing out here. Now, it's not required necessarily by the question, but again, it's an important time just to go ahead and see the different relationships that we can create with our integrals. And if you typed this lower thing into your calculator, you would also get the same exact thing.